the sky doesn't turn dark all at once. First it turns gray. Then a dull, ash-choked orange. Then a color you don't have a word for, because nothing alive today has ever needed one. Somewhere on the coast of what is now India, roughly 74,000 years ago, a fine white powder starts drifting down from a sky that, until that morning, had looked like any other. It settles on leaves, on water, on skin. It keeps falling for days. By the time it stops, it has buried the ground under a layer thick enough to still be visible to archaeologists tens of thousands of years later. What just happened to the sky? The answer is Toba, a volcano on the island of Sumatra that didn't just erupt. It detonated on a scale almost nothing in recorded human history can match. Geologists classify it as a super-eruption, a category so extreme it sits near the very top of the volcanic explosivity index, several orders of magnitude beyond even the largest eruptions most people alive today have ever heard of. Toba ejected roughly 2,800 cubic kilometers of material, enough to bury an area the size of a small country under meters of ash. Microscopic volcanic glass from the eruption, called cryptotephra, has been found scattered across the globe, in ocean sediment cores and lake beds thousands of kilometers from Sumatra. This event touched nearly every corner of the planet in some measurable way. So what did it do to the people living through it? For decades, the scientific answer was almost unimaginably grim. In 1998, anthropologist Stanley Ambrose proposed what became known as the Toba Catastrophe Theory. His reasoning started with something strange buried in human DNA. Genetic studies going back to the early 1970s had already revealed that humans carry a surprisingly low amount of genetic diversity compared to other great ape species. That's the kind of pattern you'd expect if our entire species had once been squeezed through a population bottleneck, a period where numbers dropped so low that most genetic variety was lost along with the people who didn't survive. How small are we talking? Estimates for that bottleneck are almost hard to believe, somewhere between 3,000 and 10,000 individuals, surviving in scattered pockets across an entire planet. Total. For the entire species. Worldwide. Ambrose connected the timing of that genetic bottleneck to the timing of the Toba eruption. His theory proposed a volcanic winter, a multi-year global cooling event caused by ash and sulfur particles blocking out the sun, devastating food supplies across multiple continents at once. Some estimates tied to the theory suggested average global temperatures could have dropped by 3 to 5 degrees Celsius for years afterward, enough to shorten growing seasons and stress food sources everywhere from the tropics to the far edges of the inhabited world. How do you survive years of a colder, dimmer planet with nothing but stone tools and a handful of scattered, isolated groups? According to Ambrose's theory, mostly, you don't. Global darkness. Failed foraging grounds, since agriculture didn't exist yet to fail. A species narrowly clinging to survival by a genetic thread thinner than almost any other primate alive. It's a vivid story, and it spread fast. For years, this version dominated documentaries, textbooks, and the opening paragraphs of countless articles about human evolution. It had a villain. It had a body count. It had a single, dramatic afternoon that nearly erased everyone who had ever read about it. Picture standing in that ashfall in southern India, then, believing what scientists believed for decades. The sky has gone the color of old bone. Breathing is difficult. Somewhere in the smothered distance, other small bands of humans are almost certainly dying in numbers that will, within a few generations, bring the entire species down to a population you could fit inside a modern stadium. That was the story. For a long time, it was the story almost everyone told. But what happens when scientists actually go digging for proof, in the dirt, rather than in the theory? That's where things start to come apart. Archaeologist Petraglia and his team excavated a site called Jwalapuram in southern India, almost directly in the path of Toba's ashfall. The ash layer there runs more than 2 meters thick in places, thick enough that you could stand in an excavation trench and physically point to the exact moment the sky turned to powder. If any place on Earth should show a dramatic break in human activity, a total collapse followed by silence, this should be it. It doesn't. Petraglia's team found stone tools both beneath and above the ash layer, made using the same basic techniques, showing no dramatic technological collapse, no long gap in occupation, no evidence of a population that had been catastrophically wiped out and forced to start over. People were there before the ash fell. People were there after it settled. Life, in a very literal sense, continued. Was Jwalapuram just a lucky exception, one unusually resilient group and one unusually forgiving valley? A more recent and far more detailed study, led by researcher Chad Yost and colleagues and published in the Journal of Human Evolution, went straight after the climate side of the catastrophe theory. His team examined ancient vegetation and sediment records from the southern Rift Valley in East Africa, one of the regions where early human populations were most heavily concentrated at the time. Their findings were blunt. The region shows no evidence of the severe, multi-year volcanic winter the original theory required. Vegetation patterns barely shifted. Whatever local effects Toba caused, a true globe-spanning environmental catastrophe severe enough to nearly erase humanity simply doesn't show up in the data. There's a third detail worth sitting with, because it explains something the other two studies don't quite answer on their own: why some human populations weathered this so well in the first place. At Pinnacle Point, a set of caves along the southern coast of South Africa, archaeologist Marean and his team documented a population that had, well before Toba erupted, already built its survival strategy around an unusually resilient food source, the coastline itself. Shellfish and marine resources don't disappear the way inland game or seasonal plant growth can. They're available in some form almost year-round, largely indifferent to a bad harvest season or a few years of dimmer skies. A population anchored to a coastline wasn't just eating well. It had, without knowing it, built itself a buffer against exactly the kind of prolonged disruption a super-eruption might cause. Toba, in other words, didn't need to be survived through luck alone. In at least some places, it was survived because a subsistence strategy that had nothing to do with volcanoes happened to already be disaster-resistant, built for an entirely different set of hard seasons and lean years. So here's the twist that should genuinely surprise you: the population bottleneck in our DNA is very likely real. The volcano causing it is the part that doesn't hold up. Genetic bottlenecks can come from all kinds of pressures that have nothing to do with a single dramatic disaster. Gradual climate shifts over thousands of years. Disease. Simply the ordinary, grinding difficulty of surviving as a small, scattered population across a harsh world for tens of thousands of years. Some researchers now suspect the bottleneck wasn't even one event at all, but the cumulative result of several smaller population squeezes stacked on top of each other over a long stretch of the late Pleistocene, each one shrinking the gene pool a little further, long before and long after any single volcano had its moment. The bottleneck is probably real. The single, cinematic villain we assign to it probably isn't. Now go back and picture that same scene in southern India one more time, this time with what the evidence actually supports instead of what the old theory imagined. The ash begins falling on an otherwise ordinary day, fine and pale, settling into the creases of your palms and the folds of woven baskets left uncovered outside. It's alarming. It's disruptive. Breathing gets harder, a fine grit catching at the back of your throat with every breath. Water sources turn cloudy and have to be filtered through cloth or left to settle before drinking. Some plants struggle under the sudden weight of ash pressing down on their leaves. Others, already adapted to disturbance from floods and fires long before this, barely notice, pushing new growth up through the pale coating within days. You move to higher ground if the ash pools too thickly in the lowlands, checking constantly on the very old and the very young, whose lungs handle the gritty air worst of all. You keep making the same stone tools you always have, striking flake after flake with the same practiced motion, because that knowledge lives in your hands, not in anything the ash could bury. There's no single dramatic moment where things turn out fine. There's just tomorrow, and then the day after that, handled the same patient way as the day before. Within some stretch of time, the ash stops falling as heavily. Rivers run clearer. The strange taste in the air fades. Life settles into a new, only slightly altered rhythm. Why did this specific story stick around for so long, even after the evidence stopped supporting it? Because a single dramatic villain, one volcano, one doomsday date, is satisfying in a way that a long, difficult, multi-causal squeeze lasting thousands of years simply isn't. You prefer near extinctions to have a clear cause and a clear moment, the same way disaster movies always need a countdown clock and a single point of impact. Reality, both 74,000 years ago and now, is almost always messier, slower, and far less cinematic than that. Notice how often this exact pattern shows up in how you encounter information today. A headline promises a single cause for a complex problem. A single culprit behind a complicated decline. Think about how a market crash gets pinned on one bad decision, one panicked trader, one headline, when the real causes were years of pressure accumulating from a dozen directions at once. Think about how a species going extinct gets blamed on a single predator or a single change, when the record usually shows several slow pressures arriving together. Why does the simple version always seem to win, even when it's wrong? Because it's easier to repeat. A tangled, multi-threaded cause takes effort to explain and more effort to remember. A single villain fits neatly into one sentence, one headline, one thumbnail. The appeal of a single villain isn't limited to volcanoes. It's a shortcut your mind reaches for by default, and it's the same shortcut that let the Toba catastrophe theory survive for decades in classrooms and documentaries after the archaeological record had already started quietly disagreeing with it. Your ancestors, standing under that falling ash, didn't know they were about to be miscast for thousands of years as a species that nearly died. They were simply doing what humans have always done when the sky turns strange, adjusting, adapting, continuing, and passing the knowledge of how to survive down to whoever came next. No single dramatic decision saved them. No hero, no turning point, no cinematic countdown. Just the accumulated weight of small, practical choices, made by ordinary people, repeated enough times across enough generations to add up to a species that is, quite stubbornly, still here. The sky doesn't turn dark all at once. It turns gray, then orange, then a color with no name. And on the other side of it, whether 74,000 years ago or right now, facing whatever version of that ash happens to be falling on you, the actual pattern was never collapse. It was the quiet, unglamorous, thoroughly unremarkable fact of continuing anyway.